Alright, so we're going to do a lab with standing waves in a column of air, but you know we have looked at strings, and we know that in a string, let's say we just have a piano string here, connected at both ends, that the first harmonic, the fundamental, can be set up like so, where you have nodes at either end, and here is the antinode. And you can also see that this is half of a wavelength, so that we know that the length of the string here is half of a wavelength, and the length of the string is half of the wavelength. And you can see that because, I do this in a different color, the wavelength would be like so. Okay, so that would be, if we were able to set up this entire wavelength in this little space right here, that would be, the length would be the wavelength. But we're just going to start with the fundamental, the first harmonic, and we're going to set up that. Okay, but in this lab, what we're going to do is start these standing waves in a column of air, so like an organ or a flute or something like that. So you don't need to do a formal lab report. You just have to, on a separate sheet of paper, or I suppose if you want to print this out and do it, it's fine. Just what we're going to talk about here. Okay, so let's see here. Hold on. So in this objective, in this lab, we're going to set up some wave patterns by just smacking the end of some PVC piping, and we would set up a microphone that would show the frequency, and also an FFT graph which would show the peak frequency, and we're going to look at both of those. And since we can't do it for real, we're going to I'll just show you the graph. Alright, so we're going to have some pipes here, and then first set I will just choose the length of the pipe and the diameter of a pipe. In part 2 we'll go ahead and do different lengths and that kind of thing. So what we're going to do for a pipe open at both ends is smack it with just a finger so that there's an opening here and here, and we're going to create a sound. We'll put a microphone right there. For a tube or a pipe that's closed on one end, we'll smack it, but we'll close up the end as we make that sound. And so this is going to be a pipe that's open on only one end, closed on one end. Okay, so we just talked about that in the previous paragraph. We have our nodes and our antinode here. We know that sound is longitudinal waves, but what we want to do is do a transverse graph so that we can see how these compressions, or in my in the lecture I call them condensations, same kind of thing. And we're going to look at rarefactions where the compression is not as great, the molecules are further out. So we know that the energy of the wave is going this way. We know that the molecules of the air are going this way, but we're looking at these compressions here more, and they're transverse. Okay, so just a little bit of background there, but we're going to go ahead and I'll show you how you want to do this lab. So on a piece of paper, whatever, just label this as number 1. And we are going to sketch the waveform for the fundamental for a tube that's open on both ends. And if you want to look at slide 28 in our notes, that might help you, or you could Google it. So the sketching is going to be for A, call that A, and then answer, so do a sketch for A, and then answer, how does the wavelength compare to the length of the tube? And again, if you look on slide 28 for your homework, you can see that. All right, so we're going to go ahead and unfortunately to scroll I have to erase that, but you could always rewind the video. We're going to go ahead and set up the temperature probe because, as you know, it matters what the temperature is. So we're going to pretend it's warm in our room. It probably isn't going to be, but we were to do the real lab. But we're going to say it's 25 degrees Celsius. Now, later in the lab, you are going to have to know the speed of sound in air at 25 degrees Celsius, and that is in our notes as well. Can't remember what slide it is, but maybe I'll come back to that. All right, so we also need to connect a microphone down here, and we need to smack it with one finger, the PVC piping, and that's going to be open on both ends. So the first data that we're going to collect is open on both ends. All right. The length of the PVC pipe and the diameter, let's say that we have a length. We probably measure this with a ruler at 40 centimeters and then convert that to meters. And then let's say that the diameter of the pipe is going to be pretty small, 0.022 meters. All right, so we'll start data collection. And I don't think you need to necessarily write that down. You could do a small data table, but you are going to use that in later calculations as well. All right, so as we do this, we take a run, and we start a data collection. We take a run, and then we try it a few times. Always want to do a few different trials, okay? And you will see this sine wave. So we're going to do a couple of trials, and we're going to also do this with a tube closed at one end. So before we do evaluation of the data, let's take a look at a graph, a couple of graphs. And let's look at this graph first. This would be one of the graphs that you could choose from the LabQuest or your Chromebook. And you see sound pressure here in time. And so what it asks you to do is to tap and drag across this data. And when you tap and drag it, you can see there's 1, 2, 3, 4, 5 cycles, and it tells you the time down here. So that's additional data you would have is 5 cycles in this time period. And I don't know if you can read that so well because the scanner that I scanned it in with is right there. But what it's reading is 1.01283. That's the time, seconds, that 5 cycles took. Okay. And we really want frequency, which is cycles per second. So we're going to flip that. Okay. And when you divide that, you'll get 0.00257. So what I want to do to get frequency is flip that. Okay, and we're going to get 389 hertz when we do that. So you should jot this all down as data. Okay. The other graph that I'm going to take a quick look at is, put this one down and look at this graph as well. And this is amplitude versus frequency. It's going to tell us the peak frequency. And we see here that it agrees pretty well, 390.63 hertz. And so I'm going to just average those two. So the other one's 389. This is about 391. So I'm going to average our data. What we have found is 390 hertz. And that is for a tube open on both ends. All right, so just jot that data down as well. All right, now we're going to do that again with the pipe that's closed on one end, and we're just going to have our hand cover it as we make that sound. And what we find here, and this will also be data, the tube closed at one end, and what we're going to find here is that it is 213 hertz. So when you do all that, the same thing as we just did with the tubes, or the tube open on both ends, we're going to do it with the tube closed at one end. So two graphs, we're going to come up with 213 hertz. Okay, So we've just basically evaluated the data, and you should jot all that data down. And I have to scroll down here. And it says, for the last thing that you should do here is find the ratio of frequencies. And so you'll see if I look at about 213 compared to 390, we get roughly 0.5 ratio. Okay, it's half of that. Or I guess the other way you could say is this one's twice as big as that one. So does that make sense? So what you're going to want to do in the last thing here, I guess you could call it number 4, is you've compared these two, okay? And so what is the meaning of that? And again, looking at slide 28 in your notes is going to help you make a conclusion statement there. All right? The next thing that you have to do here, and write down on this piece of paper, is to look at the tube that's closed on one end. And I guess that would be number 5 in your notes. And as long as you have these down, I guess I don't care how you number them, but this would be the 5th thing to write down. It says sketch the waveform. So that's going to be part A. And what fraction of the wavelength should fit inside, and that'll be part B. And again, slide 28 has a picture of all that, or you could Google it. All right, so there is a correction that we have to make, and maybe that correction will make the ratios a little bit better, because that wasn't really, it was really approximately a 0.5 or twice as large. So what you need to do here is for study number 6 is to correct our data, and so we're going to use this equation right here, and we'll have an effective length, and that'll be length plus 0.33 times the diameter of the tube, which I wrote down previously here. Okay, so go ahead for number 6 there, calculate the effective length, and then go ahead and do wavelength. All right, based on that. Now, what should we do for an effective if it's open at both ends? So if you happen to notice, the reason that they're doing the correction, and the reason we're doing that is it's slightly greater than outside. It's just right outside of the tube rather than exactly inside the tube. So that's where they're making that correction. So if you're going to have to do it for a tube that's open on both ends, what you're going to have to do is do it twice. So this correction will be the diameter times 2. Okay, so add that and do it twice. Okay, so go ahead and do that for the open one and then the wavelength. And then you could find the ratio of the wavelengths as well, but we'll just do the frequencies. Okay. And that's going to be a better relationship. It'll be cleaner. It'll be closer to 0.5 or 2. And so go ahead and do those corrections. And actually, if you want to just do those frequencies, don't worry about the wavelengths. Just go ahead and do the frequencies there, the relationship of the frequencies from here to here. All right. And then the next one we will do is part 2.